Just started streaming, waiting for YouTube to agree. YouTube agrees. Stand by. We got a delay. And double broadcasting. I'm switching to YouTube. Well, I'll switch to YouTube in a second. Oh, Inception. It is March 26th, Friday. No longer in Inception, double broadcasting. Now single broadcasting on YouTube and fading. Okay, and let's see, why am I hearing myself twice? All right, something is going on where I'm hearing myself twice. And I'm not broadcasting in game. And let me see what's going on. I have no idea where the sound is coming from. All right, let's see. How can I identify where the sound is coming from? I'm sorry, you guys. All right, let's see. I'm broadcasting. I'm going to talk it through. I don't know what's going on. All right, I am in game and I see no indication that I'm talking in game. So my mic is off in game. My media is not playing in game and my media is turned off in game. My YouTube is muted. None of my tabs are indicating that I'm playing sound. I'm going to pull up my sound preferences. My output is coming through multi-sound. Let me just do here, check, check. And check, check. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I cannot double broadcast. All right, let me see. Where else might my sound be coming from? It's in my ears. It's going through my mic. It's going into my broadcaster. I see the broadcaster going out. It's going to YouTube. Nothing is broadcasting. This makes me upset. My mic is turned on now. And am I hearing myself? Okay, I'm going to drop out of Firestorm for a second to see if that's the problem. All right, testing. 1, 2, 3, 4, 5, 6. All right, I'm not hearing myself anymore, so that's good. Okay, I am back in game, and my media is turned off, and my mic is turned off, and I think I'm broadcasting on YouTube. All right, let's double check. Can you hear me on YouTube? Now. Check, check. 1, 2, 3. Can you hear me on YouTube? 1, 2, 3. Check, check, check. With a little delay, but everything sounds and looks good on YouTube. All right, great. So my game is fixed then, so we can move forward. All right. Super. Good morning, everyone. Good to see you. Looking around the classroom, see Dee Dee and Trent, Ethan, Josh, Adeline, Matthew, Thomas, Taylor, Faith, Ethan, Landon, Morgan, Ben, and Monty. Good. All right, so one thing that I was doing there for a moment is I was collecting the grades from last class, and a few of you didn't get on the board. We had some technical glitches last time, so if for class 28 you did not receive credit for attending, but you were in fact attending, please let me know and I will correct that. I'm going to release class 28's grades right now. They are released. You'll get a notification in a second if you have notifications turned on. All right, the next thing is to make sure that you've checked in for the attendance board today. I just reset it, so you feel free to jump over there and check it out. We are wrapping up. So what we just came through was a discussion of the implementation of array lists and linked lists. It was a struggle. So what I've done is I've collected a set of videos for you that will walk through that again so that you can see what the punchline was about how array lists and linked lists have different kinds of performance um, properties. That's an important thing to know. It's just going to work better if I'm able to show it to you in the context of a recorded lecture because um, the complexity of getting Saros and everything running and getting the code in place was a little bit much for our current environment. Just one thing, I like when I teach these classes, one thing that I do is I do it fresh every time. I don't just rehash the same slides and everything. And so anyway, that induces some glitch, but it is a little bit better in my mind for teaching because I'm able to respond to how you folks are responding. However, it just didn't work last week. So I'm going to I'm going to put that series of videos in the notes for today after the lecture is over so that you can see that and see what, see how that was supposed to work. We need to move forward though. And so we're going to move forward talking about generics in Java. And so to do that, I'm going to present slides on that primarily. And we're just so we can get a little bit more rhythm, we're going to skip Saros. Although I am going to do some work in Eclipse, we're going to skip Saros for the time being, just because I feel like we got to get a rhythm back a little bit. All right, so let me stop for a second and see if there are any questions about anything I've said so far, anything you want to clarify about assignments or grades or anything that's confusing to you because I can't see your face and look at your look of astonishment or bewilderment. So I'm relying on you guys to speak up and say something. Okay, feel free to do as much. If you want to just throw something in the chat indicating that you have a question, as I get a chance, I will slow down and respond to that. In the meantime, what we need to do today is cover the first of 2 lectures on generics in Java. And so without further ado, let's get rolling on this. Yeah, let's do it. Okay, so generics in Java. You've used generics already, and we've called them generics, but you've always used them as someone who is an API programmer. You've always used them as someone who's using a class that implements generics, but you've never implemented them yourself. And so what we're talking about in this chapter is how to implement generics. And let me just make sure I've got Slack up as well because I've got some Slack trouble. All right, and that's from Ben. All right. Okay, Ben's following along. Great. All right. Talking about implementing a generic class along the way. All right. So at a really high level, like from the 10,000 foot level, what generics enable you to do is they enable you to use a type kind of in the same way that you use a parameter when you call a method. You have experience in calling methods and passing in data as parameters to those methods. That's something that you've done already. You've done it many times. Anytime you call a method, anytime you call a method that takes parameters, you've passed it parameters. So you've worked as someone who is a user of a class, an API programmer, you have accessed the library and you've passed data into them. What would be an example of that? Like, like the equals method requires a parameter that you pass in. The dot equals method. You've also acted as someone who has written a method that accepts parameters. So someone that has done an implementation within an object, you've written a method, you've written the contents of the method, you've implemented that method, and in the body of that method, you have used parameters that have been passed in. But so far, we've only worked with data. We've passed data, we've received data. Generics give you the ability to use types in a kind of parameterized way. So the input to a generic is a type, and the output of the generic is a new type. That's a composition of what you've passed in and what has been defined. So in a lot of ways, like parameters in methods, generics have an input and an output, but they're types, not data. They're not values. They're describing the data. And in that way, because they describe data, we call them metadata. The value of it is that a lot of times the algorithms that we write it doesn't matter what data we're using. It's a matter, what we care about is how we're manipulating the data. So, when you think about like a list, for example, it doesn't really matter too much what you're storing in the list because the idea of a list is independent from the data that you're storing in it. You put things in a list, you take things out of a list, you go to a particular point in the list, you go to the first point in the list, you go to the last point in the list, you iterate through the list, and all of that functionality is independent of the actual data that you're storing in them. And generics enable you to write that code in one place, regardless of the data that you're storing there. So the benefits are that we end up writing less code. We do code reuse, and because of that, there's less places for bugs to show up. They enable a systems programmer, to implement algorithms that lend themselves to generics once. So just generally less bugs because there's less code that you're writing. The other thing that they enable us to do is they give us some of the flexibility of a language like Python, where you don't have to necessarily designate a type, but the benefits of a strongly typed language where an IDE like Eclipse can tell you that you're passing the wrong type into a method or you're receiving the wrong type back from a method. Those kinds of errors are only possible, those kinds of compile time errors are only possible because we have strong typing. So we find more errors at compile time because of static checking. We don't have to wait to run the program to see the program crash to recognize that we have an error. We can detect them static. That's called static checking, when we check the source code without having to run it. Dynamic checking is when we have errors when the code is running. Okay, so here's kind of the world in which we're operating. We have a developer on their computer over here on the left. See if I highlight that. Can I draw on the slides? I'm not going to click on the slides for fear of what it's going to do. But okay, over here we have a developer on the left working on a computer using software like an IDE and writing some code that does things. Eclipse, working together with the Java program, will compile that. It actually compiles it while you're writing code. That's how you get those static compile time checks that light up Eclipse with red and yellow indicators on the side. If it all compiles fine, what you end up doing is you end up having this intermediate file, which ends with .jar typically. A jar file it stands for Java Archive. It also is like a mason jar, but it's an acronym for Java Archive. And this is the program that gets run. It gets run, it's machine independent. It just has compiled Java code and something called bytecode. And what you do is you send that out to distribution. So however you distribute your Java code, maybe you put that in the Google Play Store because Android programs are typically written in Java. Maybe you put it on your website for downloading. Maybe you put it in a Mac store or whatever Windows is doing for stores these days, but put it on a website. That jar code goes out for distribution. Then someone like this handsome gentleman with the scarf and the white hair receives that and runs that jar on their own virtual machine, running on their particular hardware, And because they're using a virtual machine, it doesn't matter which hardware they're running it on. The bytecode is attached to the virtual machine, not to the hardware. And so the bytecode runs on the virtual machine and great things happen. What a terrific pairing of developer and user. Developer has put in a lot of time and energy to make the computer do something, and at least one and maybe many, many more users are getting the benefits of that. Maybe it's a volunteer work, maybe it's a job, maybe it's a nonprofit, maybe there's money exchanged, who knows? That's the general idea of how the distribution happens in Java. All right, so now that is going to come back to bite us in a second without generics. So let's look at some code here. The first bit of code doesn't use generics and it requires casting. It requires us to assume that some data that's received back is of a particular type. So let's look at how this works. We see that we're creating a variable called lowercase l list. It is of type capital L list. We know that capital L list is an interface, and in this case, we're using the Java implementations of these classes. When we go to create a new instance of this list, we have to pick a particular implementation that has different kinds of performance. We choose an array list here. Array list, we choose you. So we call new, we create a new array list, we store a reference to that array list in our variable list, and we can use all of the methods that are associated with the list interface from this point on. If there are any methods that are particular to array list, we no longer have access to them once we declare list being of type capital L list. So what we do is we add something to our list, hello. By default, the add method places something at the end of a list, regardless of how it's implemented. So we add a string hello. Later on, for example, the next line, we ask to receive back the element that is at index 0 from our list. So we just added it there, hello, and we're getting something back. Now the thing that we get back doesn't have a type. We don't know what type it is. And so we have to explicitly cast it to a string in order to assign it to a variable which is of type string. S is a variable of type string. And because our list can hold anything in it, we have to assert that it is a string here. And this is an unsafe thing to do. Because if the thing that was stored in our list was not a string, for example, in the previous line, if we had added an integer or we had added a double or we had added our own custom class like a bank account or something else, when we got down to the third line and we asked for the element at position 0 to be returned to us, if we cast something that was not of type string into string type, the code would crash here. So this is going to work because we know we put a string in there, but there's no way for the compiler to know that for sure. In the second case, when we rewrite this with generics, we add support for the compiler to help us out here. So instead of just saying list can have anything, we use the generics syntax of the open brackets, the diamond syntax that we've seen, and we put in a specification of what this particular list is going to have. And this particular list is going to hold strings, and so we're going to instantiate it with a constructor call to an array list that contains strings, and then we'll call the constructor with no parameters using the new reserved word. We then get back a reference, and the compiler now, nothing has changed actually in terms of the code that's being written. But what we've done with this generic is we've told the compiler, from now on, we want you to enforce and assume that what is in this array list is a string. So on the second line, when we do list.add hello, the compiler is making sure that what we add to list is in fact a string. And it can do that now because we've asserted in the first line that what this list holds is strings. And likewise, because we have told the compiler that this variable holds strings, when we call get0, we don't need to tell the compiler to cast it to a string. We are going to get a string back for sure. And the compiler enforces that because it never allows us to put anything but a string into this list. And so therefore, everything that we get out must also be a string. And the compiler gives us support for that now because we have used the generic. So we have no cast there. And now it's no longer an unsafe situation. We're not worried about S being assigned to a bank account or an integer or a double because nothing but a string can get put into that list. And that's good. That reduces the amount of errors we can potentially have. So let's take a look at this particular code. Now I know that it's a little bit low resolution. So let me zoom in for you here. If we were in person, I would have you break up and to look at this code and to try and evaluate what's different about it. Um, don't have the capacity in game to do this quickly. We actually do have the capacity to do it, but it would take more work than I had time to set up for. So in lieu of thinking about what it's doing, talking about it with a partner here, let's look at it individually and ask the question, what does the code on the left do? What's different about the code on the right? And is the code going to compile? So let me zoom in for us for a second and take a look at the code on the left. I'm going to give you 1 minute to evaluate this code on your own and to identify what it does. One thing that we haven't seen yet is the vector type. Um, the only thing you should really need to know is that a vector is another kind of implementation of a list. So a vector implements the list interface. It's a different way of doing it. And so the way vector works is the same way that any list works. So let me give you a second to look at that, and I'll stop talking for a moment and give you a minute. Okay, so let me have everyone use the chat function in game to describe what they think that this code on the left is doing. And let's see, I would like to let you continue to see that while we look at what answers come in. So actually what I can do is I can put it side by side. But I can't simultaneously zoom in. Okay. Okay, Sam asserts that it's going to print all the words in a list that are longer than 4 letters. Ethan and Matthew agree. Josh says that we're going to make a vector full of 5+ letter words and then print them. So, yep. Adding the fact that it's getting printed out, that's an important chunk of that second loop. All right, for those of you that aren't speaking up, let me give you a chance to look at it again and make sure that you agree with that. And when I say speaking up, I mean typing. Sorry, I find that funny. Okay, so take a look at it again. The assertion is that it's taking input and it's printing out all the words, or it's storing all the words that are 4 or that are greater than 4 letters long, so 5+, and then it's going through and printing them. All right, so if you agree with that, go ahead and just throw something in the chat so I know you're following along. Okay, good, great. All right, so now let's take a look at the code on the left, the code on the right. The code on the right has been labeled bad code, and so there's something wrong with this code. Um, if I leave it like this, is the resolution okay that you can see it, or do I need to zoom in? Okay, mixed bag. All right, so let's zoom in a little bit. Let's see if I can go. Okay, that's probably about as good as I can zoom and get it both on the same screen at the same time. There we go. All right, let me give you a second to look at that. This is like playing a game in a kid's magazine. What is the difference between the code on the left and the code on the right? When you see it, throw it into the chat. All right, looks like I hear some typing. I can't see what you're typing at the same time when I'm zoomed in like this. So let me zoom out, see what we're saying. Oh, you know what? Yeah, I can do that. I just put that up here. Okay, great. That's better. Great. Now I can, in a moment, I will be able to see. I'm rearranging my windows for a moment so that I can see chat at the same time. Great. All right. All right. So the correct answer that yeah, some of you all have indicated is that the code on the left has args bracket I being added to long words. And so what we're adding to long words is strings. Long words is getting arg sub I, so a string is being added. But on the right, each thing that's being added is the entire array of strings. And so on the left side, if we think about a vector as being a boxcar, like a list as a representation as a train, represented as a train, where each boxcar is where we're storing the data. On the left, the boxcar called long words, each container has a string in it. But on the right, the boxcar that we're calling long words, each container has the entire array of strings in it because we added args, not args bracket I. All right, so that's fine. Like both of those codes are going to compile fine. Maybe you have a program where you want to store arrays of strings in each element of your list. Maybe you have lots of arrays of strings. Like you could imagine that you have an array of strings. You treat a sentence as an array of strings, for example. The quick brown fox jumped over the lazy brown dog. That's an example of a sentence where you could keep each word in an element of an array in a string, and you could store that entire thing in one boxcar. And then a second boxcar could have a string like the quick brown fox was eaten by the fast and aggressive dog Dodger. And that string could be in the second boxcar. So there's nothing about a list interface, in this case a vector, that prevents us from storing an array of strings in them. It's just that you have to choose what you want to do. So on the left side and the right side, on the right side, we have a mismatch in context, though, because it doesn't seem to be doing the work. What it's doing is every time it encounters a word that is greater than 4 characters in length, it is storing the entire array in that boxcar associated with the word. So it's like not doing effective work, but it's not doing something that is syntactically incorrect. So the code on the left, to reiterate, is storing all of the words in the parameter args that are greater than 5 or more characters in the vector long words, and then it is going through one at a time and printing them out. The code on the right is doing the same thing, except that it is adding the entire string each time and then printing it out. Um, the problem is, okay, so fine, it's syntactically correct. Yeah, so Didi, your comment is another way of saying what I'm trying to say. All right, so here is the situation now. With the particular code that we're just looking at, The programmer created some code, it compiled it, it went to bytecode fine, it was distributed, it went out to the channels, the Play Store, the website, whatever you've got. Handsome gentleman with the scarf and the gray hair tries to run the program, and the whole thing is going to crash. But it's crashing at runtime, which is over at the right. There's no support over on the left to detect that error. And where is the crash actually happening? So let's see. Let's go back and let's try it out. So let me go to Eclipse. I'm not going to do Saros. I'm just going to show you my Eclipse. Boop, 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 boop. And where did I put my code? Here's my code. Let me save it up. All right, so we've got the good code at the top. We're not on screen. All right, should be the same. Good code, vector. I'm getting yellow. I'm getting the yellow because I'm not using generics, and the compiler's like, sure, you don't want to use generics. Generics are pretty good. I think you should use them, but I'm not, and I don't have to. All right, so now down here in the main function, we're going to act as the API programmer. We're going to create some test data. Fuzzy Wuzzy was a bear is our array of data that we are creating, and we're going to call the good code with that. And so what we expect it to do is to pull out all the words that are greater than 4 characters long and print them out. And if all goes well, that'll work. So let's run that code as a Java application. And let me save and let me bring it up a little bit. And we're looking for the answer in the console. And I'm not seeing the answer in the console, and I'm wondering what's going on. So I'm going to come up here and I'm going to check it out. All right, let's see. Did it just not run? What did I do? Oh, I don't have console selected. That's funny. That's funny. Haha. Look how resilient I am. All right, console. Passed in Fuzzy Wuzzy was a bear. Looks pretty good. Couple words there greater than 4 characters. Let's add another one in just to make sure we understand what's going on. Fuzzy Wuzzy was a snake. We decide to run that again. Our code pulls out snake as well. Okay, any questions about how that code just ran? All right, so now let's shift over and go to bad code. Bad code also compiles, you can see, but here's the situation. We're adding in the entire array every time we encounter a word that's greater than 4 characters. So we run this. This is the smartly dressed gentleman with the gray hair is at their computer and about to run their program that has been developed for them. They're running it, and oh my gosh, it crashes. Why did it crash? Well, we can dig down and we can say, okay, well, it crashed at line 39, so we called 39, we dig into that. 31, it crashed at 31. And here's exactly the problem. What we stored in long words was not a string. We stored an array of strings. And when we tried to cast an array of strings into a string, we just can't do it because an array of strings isn't a string. And so when the runtime virtual machine attempted to do that, we got a crash. And so that puts us in the situation that we don't want to be in. Okay. So what we can do instead is we can implement this with generics. And generics give us the ability to, hang on one sec, stand by. Okay, when we implement this with generics, we add the generic type in there. So the left side is the good code that we had before. The right side is the code with generics. What's different? What's different on the right? Yeah, throw it in chat when you see it. So just from a textual, yeah, so just from a textual standpoint, the type of long words is different. The type of long words has been provided with a generic instantiation, the string, as well as when we called the constructor, we provided something in the brackets as well, string also. So we don't need to do any casting. We didn't need to do any casting before either, but what's happened now is that the compiler is providing support. We don't see any support yet because we haven't made any errors here. But here's what's different. If we do the bad code with generics and we instantiated it with string, when we came down here to long words and we tried to add args without the brackets, the compiler says, wait a second, you said what you're putting in here is strings, not arrays. So there's a problem here. And in fact, it's a problem that's specifically against your design. And so I'm not going to compile it. And so the compiler now is giving us support to check that error because it was in fact an error. And so now when we go down to the bottom, and we don't need to cast that anymore because we know it's been parameterized with strings, but we just get caught, like the compiler supports us from making type errors along the way. All right, so this is what happened then. We added our check-in. Happy programmer is programming away. We get to the compiler stage. The compiler stops us from distributing our bad code, stops us from having a runtime error, tells us exactly what's wrong because we gave it a hint using generics about what it was we intended to do. So this is like another great reason why generics is good. In addition to enabling us to write less code, which I haven't proven to you yet, it also stops us from having errors much earlier in the distribution chain as well. Okay, so the thing that's super cool about this is that when the person wrote this code, when the person who implemented vector wrote it, they had no idea what it was going to be used with. They didn't know it was going to be used with strings. So over here on the left, we have the code with strings, what we've been working with so far all along. Let me zoom in a little bit. All right. But over on the right, we have the same vector class being used with some kind of custom class called identity. And so rather than on the left, where we check for the length of what's in our vector to be greater than 4, on the right, we're checking to see whether the height of the person that we're storing in there is greater than 6. Presumably it's in feet. All right, so we add tall people to our vector instead of long words. And the person who wrote vector has no idea how this is going to be used, but they were able to write the code in such a way that it could be used by both long word finders and tall people finders. That's kind of super elegant and pretty cool. You could use vector with any class because what vector is doing is just keeping track of boxcars in a train like any list. And what you store in the boxcar, it doesn't really matter to the person who's operating the boxcar. All right, so here's an example of a simple identity class that we might use to support that. You can see that it has 3 instance variables, a name, a password, and a height. Just as a side note, this is not a good way to store passwords in real code. I'm just doing it for teaching purposes. You should always store passwords in an encrypted format. Nevertheless, for the purposes of demonstration, we're going to do this. And you can see that we have a constructor that takes in a name and a password and just keeps that, whatever is passed into the constructor, stores it in the instance variables. That's just kind of straightforward. We have a getter that does get name. We have a setter that sets the name. So that'll change what's being stored in the contents of our class. We have a getter for our password. Turns out we also have a setter for our password, but the way we implemented that is we required someone to send in the old password and the new password. So if you want to change the password, much like a website, you have to pass in the old password, make sure it equals the existing password before we'll update it as well. And you can kind of see how that works with a little check. So our setter isn't trivial in this case. We also have a getter and a setter for our height, and we're storing that as an integer. That could probably be better done as either, probably as a double, but anyway, for teaching. All right, so let's just review the different components of a method signature so that we understand how generics end up here. So for starters, the components of our method signature is we've got its visibility. If it's public, it can be used by an API programmer. If it's not specified, it can be used depending on which package is calling the class. And if it's private, it can only be used within the body of the method. Next thing we've got is the return type, Boolean in this case, and this is a primitive type because it's a lowercase letter. We've got the name of the method, so the name of this method is setMethod. And then we've got the type of the first parameter, which is string, the name of our first parameter, old password, and then we've got several different things here. Sorry, let me go back for a sec. So the name of this, the fully identified name of this method is going to include the class name and the package name, which is identity, and then it's going to include the method as well, and it's going to include the parameter types as well, the return and the type. Sorry, oh shoot, I have to redo the animation. Sorry. All right. So what generics then end up being is a tiny little language within a language for declaring types. Anytime there is an opportunity to enter in a type, we have the ability to use generics in that location. So anytime we can specify a type, we can specify a generic. So in our particular example, we are clever hackers and we want to let people have not just a name, but a first and last name. So we're going to update our identity class to support that. All right, so this is what we've got right now. We've got a name and let's see. Yep, this is what was present. Where did I change it for? That looks like it's the wrong thing. Shoot. All right, let me see if I've got it. Give me a second. Let me see if I can find it in Eclipse. I think I screen captured the wrong thing. One second, and I'm looking for my identity class. Okay, we're just going to move on. So what we want to do is we want to have someone to be able to store their first and last name. Right now, our capacity in our class only allows us to store a single string. Now we can jam the first and last name into that particular string, but we know as people that first and last names have meaning and we like to sometimes treat them separately and independently. We like to be able to sort by a last name versus just sorting by the entire first and last name. Maybe we want something that's friendly and we just want to print out first names. Maybe we want something more formal and we want last names. Well, we know that we can do this. We can there are pairs of things that we want that aren't just first names and last names. So let's abstract this into a helper class that we're going to create that's called pair, P-A-I-R, a pair of things, like a pair of cards. All right, so here's what our helper class is going to be. It's going to be called pair, and in it, we're going to have two instance variables, the string for the first name and the string for the last name. We're going to have a constructor, which when we construct a pair, we store its first and last name, and then we're going to have getters and setters. Get our stored first, and get our stored second, set our stored first, and set our stored second. So the way that this is used is someone uses a pair class to keep two strings together by calling the constructor, and then in the future, if they want to change the two things that are stored together or to find out what it was that are currently being stored, they can use the getters and setters. All right, so that's a pretty straightforward class. So now we're going to put those two things together. So zoom in a little bit. On the left, we have the pair class that I just described, and on the right, we're using it now. So instead of storing our name as a string, the instance variable at the top is now a pair class. And we're going to ask people who call our identity class with the constructor, who construct a new identity class, they're going to pass in the first name and last name and a password. three different things. And then when we use the constructor, we're going to put those first names and last names together. So the person who's calling identity doesn't know how we're storing it, but we're choosing internally to store them as a pair. A new pair, first name and last name, and we're storing a reference to that. And so when someone asks for the name in the second method on the right, get name, we use our instance variable. We make a method call to get the first element from our stored name. We put a space in between the first and the last name, and then we call the method get stored second to get the second name out. If we want to set the name, we ask the user to pass in a pair, and we just update the pair. And then I think that's everything that's changed down here. Yeah. All right, so let me stop for a second and see if there are any questions about the architecture of this little move that I did right here. All right, hearing no questions, I'm going to move on. Now, the thing here is that the pair class is just storing two strings. So you could use that pair class anytime you wanted to store two strings. That would be fine. We happen to be using it to store first and last names. Okay, so great. Mission accomplished. Troubling words to ever say. If you ever say mission accomplished, be very careful. Well, good news. Word has spread far and wide that you are an exceptional programmer. You are tremendous at creating architectures for your code. It's elegant and efficient. And you've been hired by an EMR, an electronic medical records company, to augment their medical records. That's great. They want us now to our identity class to augment it not just with the first and last name, but with height and weight so that they can calculate BMI or body mass index. And they want that to be part of one person's identity. Sounds like another pair, no problem, height and weight. We've already done that, so it's going to be a simple fix. We're going to add that in. And so we'll store a new instance variable called stored BMI. That will also be a pair as well. And when our identity is called in the constructor, in addition to a first and last name, we're going to ask for a password, and we're going to ask for the height and the weight of the individual. And in the constructor, we're going to create a pair with the first name and last name, and then we're going to create a pair with the height and the weight. But oh no, we're being stopped. We're being stopped because our constructor that we wrote only takes strings. So the first example, we're passing in strings, and that's fine. But the constructor in the second example, we're passing in doubles, and that doesn't work for our pair class because our pair class, we defined it as taking strings. All right, well, that's a nightmare because we also get this problem down here, which is when we implement our method to get BMI and we try and get the height and the weight out to calculate BMI. So this is the formula for BMI. You take your, let's see, you take your height. I can't remember what it is. I think it's height divided by weight squared, but you have to use metric units for it. You get to use metric units for it, and so you have to do a little conversion. But none of this works because in order for the formula to work, you have to have numbers. And what get stored second does for a pair class is return a string. And so the whole thing is just borked because it's expecting the pair class is written with strings, but we're trying to use it for doubles. It's a whole disaster. We're trying not to let anyone know that we're having this problem because we were just hired by the EMR company because we're so talented at writing code. Our talent has hit a brick wall. Okay, it's all right. We've done it once, so we're just going to make another pair. We're just going to rename it. We're going to call it pair double double. And we're going to put two instance variables in there. It's a different name, so it's no problem. And we're going to store doubles, and our constructor will have doubles. And when we get our stored first and we get our stored second, what we'll return is doubles. And great, we've solved the problem. We have solved the problem by writing another class, double double. Does anyone recognize this? What is currently on the screen? This is so great. This is how you know I'm a father. You want, but what is it? Come on! What is it? It's not just a double double, it's a pair of double doubles. It's so good. It's so good. That's what we just wrote. Oh, so good. Oh, you guys missed it. It's too early. You need to drink more coffee. All right, it's a pair of double doubles. Conceptually, though, our pair class is completely agnostic to what type gets used with it. It didn't care that it was doubles or strings. The functionality of it was exactly the same. But the Java language is tying our hands. Like, we can't do anything about it because we had to specify which kind of class we were storing in it and then what kind was being returned. And so this is an example of a motivation for generics, right? This is why we want to be able to use generics, because the implementation of pair just doesn't matter what type it is. So generics are going to let us manipulate our parameters without knowing beforehand what type they are, but without losing the static type checking that you get in the compiler. So Python, for example, allows us to manipulate parameters without knowing what their type is, but Python doesn't give us static type checking. So Java, one-upping Python because it is a better language, enables us to do that. Here's how we do it. In our definition of our pair, we're going to give it a name that separates it from an initial pair. We'll call it pair generic. And now this is on the implementation side. On the implementation side, we say, when you call pair generic, we expect it to come with two types. A type that we're going to call F and a type that we're going to call S. When you, the API programmer, call our generic, you're going to need to fill in something for F and S. But when we work with it as an implementer, we're going to ignore exactly what F and S are. We're just going to be clear that they're separate types. And so we declare our first instance variable as being of type F, stored first. And we declare our second instance variable as being of type S. And when you call the constructor, the first thing that comes in has to be of type F. And the second thing that comes in has to be of type S. When we call our getters, what gets returned when we call get stored first is something of type F. At our implementation time, we don't know what F is going to be, but we know that it's going to be consistently the same type at all these different places in our code. Likewise, S, when we get our stored second, that's going to be returned of type S. And if we want to reset it, like the last method here, set our stored second, well, what you pass in has to be of type S as well. So we're consistent. We know that it has to be a particular type, and we know that particular type has to work in all these locations in our implementation, but we're agnostic to what it's actually going to be when our API programmer calls it. So now we can implement this identity class, this EMR class, using the same code, but with generics. So when let me zoom in for us. When we declare our first instance variable stored name, we say, oh, well, this is going to be a pair, but what it's a pair of are two strings. Okay, so it's okay that the F and the S are both the same type, but they're treated differently in the implementation. They could be different, but we're going to say we want them to be the same type. Our stored password is still a string. Don't do it that way. And then our third instance variable is going to be a pair, but it's a pair of two doubles, double double. Love it. Think about it. And then we're going to call that our stored BMI. And now when we call our constructor, trying to zoom out a little bit, get my mouse back. Come on, mouse. Come on, mouse. Come on, mouse. Okay, all the way. Okay, when we call our first constructor, we pass in our first name. We pass in our first name, we pass in our last name, we pass in double height and double width, and then when we create our instance variable, we have to create a new instance of a pair generic. We specify what it is we're going to store. Java takes care of making sure that all the strings internally match up and all the doubles internally match up, but uses the same code in both places. So now we don't have one thing that's pair with strings and another thing that's pair with double doubles, so that we could make a mistake in one and not the other, or realize we have a mistake and have to go back and fix them in both places. There's just one code base. So much less likely we have problems. Further down, you can see, for example, when we get our BMI, we now don't have to do any casting and we don't have to worry about whether our types are mismatched or anything, because when we declared stored BMI, we declared it as being doubles, and we declared in the implementation that get stored second is going to return whatever that second type was in our declaration, double. And so we get back a double and we can calculate our BMI correctly. But up here in get name, when we say get stored first, this doesn't return a double. This returns a string. So stored name.get stored first returns a string. But the code is no different between this method. Stored name get stored first, or stored BMI get stored second, or rather the second one, stored BMI.get stored first. These are both the same method calls, but the compiler is saying, hey, when you declared stored name, we know it's a string, so we can attach it to a string. And when you declared get stored BMI, you declared it as double double. So we're going to get a double back, and so we can multiply it and do math with it. The compiler verifies that all this is correct. So any errors that we make, any typos we make are going to happen right now at static code writing time, not later on when the handsome gentleman with the scarf runs our code. Now, mission accomplished. And what you've seen there is 80% of everything that you need to know about generics. That is the bulk of implementation. The rest is just making sure that you're just having some examples of writing it. You don't write these super often, but I have written them before. There are a few details that you need to know, and that's the last 20%. And I'm looking at our time. I see that we have 4 minutes left, and yeah, let's go ahead and do it. Let's do the last 20%. First thing to know is that generics and primitive types don't play well together. This is a picture of two children having a pillow fight on a bed, and they're not playing well together. You can't use primitive types in generics. For example, you can't do a pair of lowercase I ints. You have to use capital I integers, which is the object-oriented version. So we're building on the whole idea of objects in order to be able to make these generics work. You can't use generics in an array because arrays are basically a primitive type. And so you can see down in the bottom, it seems to suggest that what we're trying to do is create an array of pair generics, double double. You can't do that. You have to, you can create a list of them, like an array list of them, but you can't create an array. And so the big takeaway from this is that generics and primitives don't play well together. You can't use arrays, you can't use primitive types. They're a purely object-oriented innovation. The next thing is to know that sometimes as an implementer, you care a little bit about the type that gets used in the generics. You want a lot of flexibility, but you don't want it to be entirely free of constraint. And so you can put a few kinds of restrictions on what type gets used. So for example, here's an implementation where I say it's sort of generic. And what I've done here is I've put some restrictions on the type. So for example, F extends number. What that means is that when someone uses our pair class, it can be any class that descends or inherits from the number class. So it can be an integer, it can be a double, it can be any other kind of number that maybe has been implemented. Those are all possible, but it can't be a string. So the way that we say F extends number says that F can be some things, but it can't be everything. And you might need that because somewhere down in your code, you might want to do a math expression with F. And you don't care whether it's an integer or double, but it is a math expression, and so you need to make sure it's a number. You can do it more complicated things like say S extends pair double double. So S is inheriting from a class that you wrote, pair double double. So it could be a pair double double or it could be something else. It doesn't really make a whole lot of sense in the context of this code, except that you can see down in the bottom method, scale it. You can see that what we're doing is we're taking the stored first value as a double and we're multiplying it times the stored first value. So we're kind of squaring, the element. And so in order to take double value, in order to call that method double value is declared in the number interface. And so if we're going to call a method like double value, stored first must have it implemented, and the place where it's implemented is in the number class. So we have to restrict what F is to include an interface that has that double value. And if you don't do that, Eclipse, I think Eclipse will catch that for you on static time. I'd have to double check that. All right, we'll stop here. This is where we would move into a process of implementing our own from scratch. Now that we've seen an example, this is a good place to stop, both because we're out of time and intellectually. Um, Thanks for your attention. I'll stick around for a moment to see if you have any questions. And if you have any questions right now, you can throw them in the chat. Um, yep. So I feel like I need some closure here. I love generics. I like the Java language. I think you can see that. Um, I hope that that enthusiasm for programming generally is infectious. I get super excited about different kinds of architectural hacks like this. This is pretty neat. So, all right, that's it. Go in peace. You're welcome.